Sai, we are now on YouTube, so you can now start.
Okay, so do we wait like a minute or so?
Should I share my screen now?
Yeah, so I think I can first do the introductions and then we can get started. So it seems that folks are still joining since we are just 11. But let me get started with introductions. Hello to all the participants. Welcome to the second space webinar. And so this webinar is being supported by the IEEE Computational Imaging Technical Committee and also the IEEE Signal Processing Society. And on behalf of the organizers, I would like to welcome all of you to our second webinar, which is which will be given today by Laura Waller. And let me give a brief introduction of Laura. Laura is the Ted Van Duzer Associate Professor of Electrical Engineering and Computer Science at UC Berkeley, a Senior Fellow at the Berkeley Institute of Data Science, and she's affiliated with the UCB-UCSF Bioengineering Graduate Group. And she received all her degrees, bachelor's, master's, and the doctorate degree from MIT in 2004, 2005, and in 2010, respectively. She was a postdoc and lecturer of physics at Princeton University from 2010 to 2012. She is a Packard Fellow for Science and Engineering, Moore Foundation Data-Driven Investigator, OSA Fellow, and Chan Zuckerberg BioHub Investigator. She has received the Carol D. Salk Distinguished Graduate Mentoring Award, Agilent Early Career Professor Award finalist, an NSF Career Award, and also the SPIE Early Career Achievement Award. And her talk today is going to be on end-to-end learning for computational microscopy. And without further ado, let me turn over the mic to Laura.
Great, thanks. You can see my screen now. And so thanks for inviting me. I'm going to talk today about my group's work in computational microscopy and focusing on a particular project, this DiffuserCam that we've been working on various different architectures and aspects of. So I think everyone here knows what computational imaging is, but let me give you sort of my definition. It's this co-design of hardware and software for designing imaging systems that take advantage of both. So I think this is a really important and a prominent trend in microscopy that instead of it being all about the optics, we now have to think about the software just as much as the optics or more in some cases. And there's really cool things that you can do by using the computation to replace optics or to capture images that are indirectly measuring the things that you want to reconstruct in the end. And there's a lot of really interesting work going on in this space. One of the newer areas that I'm really excited about is not just using computation to reconstruct images from data you've captured with your hardware, but to also use data-driven design to design the hardware and find optimal ways of encoding the data such that you can do inverse problems that are well posed and recover the most data. So let me start with like a typical pipeline, and this is the DiffuserCam project. So it's a lensless imager. So you take a camera and you remove its lens and take a picture. So it's just a sensor pointed at the world. The picture looks like garbage. And the question is that, can I reconstruct an image from this? Because these light rays that hit the sensor are the same ones that would have hit the sensor if I had the lens there. The lens's only job was to bend those light rays. And so if I can do that computationally, I can potentially reconstruct the scene from this measurement. In practice, it's far too ill posed. This is never going to really happen. What we have for this DiffuserCam is that we stick a scattering element in front of the sensor. So it's just a bumpy piece of glass. You can literally use the stickers that you put on your windows so your neighbors can't see in, this privacy glass sticker. and paste it onto a sensor cover glass and take a picture. And the picture still looks like garbage, but now it's structured garbage. And we can invert the problem and reconstruct the scene. So I want to get into the details of this DiffuserCam project. And you'll see there's a few different architectures. But let me talk for a minute about lensless imagers. So a typical imager camera has a lens that focuses a point in the scene onto a point in the sensor. So the system's impulse response or point spread function is a point. And the best system you have is the smallest point that you can create from for this point source. So it'll give you the highest optical resolution. These mask-based cameras just get rid of the lens and map a point in the scene to some weird pattern on the sensor. Since they're lensless, that pattern will cover the whole sensor unless you put an aperture. In this case, I'm just showing a designed amplitude mask. And so its point spread function will have this crazy design that's been patterned into it. There's been a lot of really interesting work, particularly recently, in using mask-based lensless imagers because they're compact and cheap. So they're a lot thinner and lighter weight, and these masks can be made very cheaply to do 2D imaging or photography. Our DiffuserCam is one of these mask-based imagers, but the mask in this case is a phase mask instead of amplitude mask, and it's a random phase mask. So it's just this bumpy piece of glass. So it looks like the bottom of a swimming pool when you look at this point spread function that it creates. And it's the same idea as random caustics. And we try to choose a diffuser such that it's placed at a distance that corresponds to its caustic length, which is sort of like the average focal length of these bumps is the best distance to place this diffuser away from the sensor. So you get sharp features on the sensor, but they're still spread out in the way that you always get with these lensless mask-based sensors. And we're going to be able to use this point spread function to invert the inverse problem and solve for the image. I have my two awesome undergrads from my lab, Camille and Trias, came and took this project and did it on a Raspberry Pi with double-sided Scotch tape just to make it really cheap. So this is terrible quality imager, but it's very cheap. And they made a neat tutorial that you can find on our open source website if you want to make this with your kids on the weekend or with yourself. And if you do, please send us images. We love seeing what images people get out of it. They're never good, but it's fun to do. So this DiffuserCam, however, can be a good imager. And if you use a better sensor, you can do better. But what I want to get into is how it works. So if you think about a point in the scene lights up and you get this diffuser pattern on the sensor. If I move that point in the scene, what happens to the sensor pattern? Well, it simply shifts. So because it's a thin diffuser and it's very smooth, it obeys paraxial optics. And so we get this sort of pure shifting. If I turn on 2, I get the linear sum of their responses. So this can be written as a really nice linear inverse problem that's shift invariant because the point is just shifting is causing a shift in the PSF. So your traditional camera, if you want to write it as a linear system, you have this forward model A that's mapping your measurement Y to your scene X, and you're trying to make A an identity matrix. That's like the whole goal of optical engineering for a very long time, for many centuries. Computational cameras are very different. We don't care if A is identity matrix. In fact, we probably want it to be something else, as long as it's invertible and known. And so now our measurement can be some crazy mess of scattered light, but we can still reconstruct the object if we have these properties on A. So we need to know A, this forward model. That's a problem because we're trying to reconstruct high resolution images. So even for this 2D photography case, we might have a 5 megapixel sensor trying to reconstruct a 5 megapixel image. So A is actually 5 megapixels squared. So measuring it by putting a point in the scene and moving it around is pretty infeasible. It's just too much work. We also want you to build this at home with your kids, so you're not going to have a precision motion stage to go and move that point source around in the scene correctly. That's where the this sort of shift invariant model is really important, because that means that the whole A matrix is defined by a single column of this A matrix. We also can't model this thing. We don't know the surface shape of this diffuser, so we can't just model that. We could go measure it in an AFM, but that would also be very expensive and make this really difficult to replicate. I'll show you later, we can machine learn it, and there's pros and cons to that. So the beauty of this sort of shift invariant model is, so as we go to different lateral positions of that point source, that point spread function is just shifting. As I move axially, it's scaling. So actually I can predict the response of the system for any 3D position in the scene of a point source, just by shifting and scaling a single calibration measurement. So I just put a point source in the scene, just my iPhone flashlight, and take a calibration image. And that's all the calibration we need to do to know the entire A matrix, because it's convolutional. So this A matrix is just a bunch of columns that are the same but shifted. You can see here some of the point spread functions. So there's one complicating factor that we have a finite size sensor, and so these point spread functions get clipped as you go to the edges of the field of view. And so it's not exactly a convolution is what I'm saying, but you can deal with that fairly easily, and we do. So our solver is ADMM in this case. We use total variation regularization just for denoising. It's all written in halide, so it can be fast. And here's a raw sensor data to a recovered scene. So this is basically just a little bit of fancy deconvolution, and it can all be done sort of in real time on a laptop. Here's a pretty image, and then a video. And part of why I like to show this video is because it's got some artifacts. And I think that these sort of point to where we're going with this sort of project. And you can see there's artifacts here, and they're almost surely due to model mismatch, that our point spread function that we measured wasn't perfect, and that maybe something moved, so the sensor heated up and that diffuser softened up a little bit and moved. And so we could go after fixing all those and trying to get a really high quality photographic image, but that's not where we wanted to go with this. We just didn't see this as something that's going to replace the camera in your cell phone, because those cameras are already extremely compact and extremely cheap, and getting to that quality would be really difficult for this kind of computational camera. So we wanted to go in a direction that computational cameras really have a big advantage over regular cameras. And that was really thinking about higher dimensional things. So one of the huge benefits of these lensless cameras is that they can multiplex. So a point in the scene maps to a lot of points on the sensor. And if you have sparse high dimensional things that you want to measure, you can potentially multiplex them into a two-dimensional image. So here we're going to multiplex two spatial dimensions in time into a two-dimensional image, and then use compressed sensing to reconstruct the three-dimensional space-time cube. And this was really an opportunistic project. This was something that my student Nick recognized and got his undergraduate summer researcher Patrick to work on. And they said that because a rolling shutter captures only a line of the image at a time, we actually can get information about the entire scene from every line measurement as you do this rolling shutter exposure, because every point in the scene maps to a lot of pixels on the sensor, and every line in the sensor actually contains information about the entire two-dimensional scene. So where it's relatively sparse in some basis set, you could potentially take a line measurement and reconstruct the entire 2D scene. So then if you take a rolling shutter, which measures one line at a time at an extremely fast rate, probably 1,000 times faster than the frame rate of the sensor, then you can potentially get a video from a 2D image that's captured with a rolling shutter. And that's exactly what this is. So on the left, you see the raw data that we captured. And then on the right, you see the far right, you see this video that we can reconstruct. If we had tried to just reconstruct normally as if this was a static image, then what you get is motion blur as expected. But now we can reconstruct a couple hundred frames from this single raw captured image, which I thought was a really cool demonstration of the properties of this multiplexing. Here's another example, a raw video. This is an important scientific application of Nerf darts hitting apples on textbooks. Hopefully you can see the video okay over Zoom. And so moving on, the sort of obvious higher dimensional space to look at is 3D. And this is where this DiffuserCam really does well. So the main reason it does well is because we get this like scaling response as you go to different depths. And this is really different than a regular camera. So a regular camera, as you go off focus, everything just blurs. There's one focus plane and things that are not in focus are blurred, and there's really nothing you can do to invert that problem. That kind of blur is lossy, so you're losing spatial frequencies. Whereas here, you're not losing spatial frequencies at different depths. You're just getting a different response that also has a fairly high spatial frequency features in it. And so we can have a chance to do this 3D reconstruction. So this is also going to be a highly ill-posed problem. We're trying to take, say, a megapixel sensor, Y, and reconstruct now a megapixel at every depth for, say, 100 different depth planes. So we've got a factor of 100 underdetermined system. The A matrix is really easy to build because it's just these convolutions with different point spread functions for each depth. And that helps us a lot with computation and calibration, but it doesn't help us with this problem being underdetermined. So the solution to an underdetermined problem is to make some assumptions. And so we're going to use compressed sensing. I think this audience is pretty familiar with the concept of compressed sensing. If you can make a prior assumption that the sample is sparse in some basis set, then you can get away with reconstructing more voxels than you measured pixels on your sensor. And I'm just going to show an example to show you how amenable to compressed sensing this DiffuserCam system is. And it's all because of the multiplexing. So your raw image makes this reconstruction, and then I just throw away 80% of the pixels in the raw image, choosing randomly, and my reconstruction still looks good. I can throw away 90%, even 98% of the pixels being thrown away still gives me sort of a rough image of Grace and her Thorlab's dog here. And this is because every point in the scene maps to lots of pixels. So throwing away some pixels is not that big of a deal because you still have information from all parts of the scene. So we can use this not to throw away pixels, but rather to use a 2D set of pixels to reconstruct a 3-dimensional scene. And here you see in the top left is the raw image. The gray image is the raw image, single image that we capture. And here you're seeing the 3D reconstruction, and I'm simply spinning it for visualization. So you can see that we have good depth information here, despite being a single shot image. So this is a little leaf, and it's brought fairly close to the sensor. This whole system is extremely not telecentric, and so the resolution and the sort of depth quality that you get is very dependent on how far away from the sensor you are. And I'm not really getting into those details, but I'm happy to answer questions at the end. But I think where this is really exciting for microscopy, which is the space that my group generally works in, is that it's not like these other 3D methods. So if you have a point scanner, so confocal microscopy is point scanning basically. And so you can get great resolution with that, but terrible speed because you have to scan a point. And you can get fancy hardware to make it faster, but you're fundamentally up against this. The bigger volume I want to measure, the slower this whole thing is going to be for a given resolution. Lightsheet is scanning a plane, so a little bit worse resolution, but faster speeds. And then light field microscopy is always single shot, so it has really good speed, but terrible resolution. And that arguably resolution is the only reason to use a microscope. And so that sort of isn't very practical. This DiffuserCam approach, because it uses compressed sensing, has a whole range of resolution. So it's always fast because it's single shot, but the range of resolution depends on how sparse the thing is how good a resolution you can expect. And of course, the optical design, which I'll get into a little bit more later. But for microscopy applications, this is really key because we have a chance to be in a world where we have both the speed and resolution that we want. And one of the big applications we've been pursuing with this is neural activity tracking. This is just an example with a zebrafish. Mice is sort of the more difficult and exciting space where we can work on this. But the idea is that you can localize each neuron in 3D. So this video on the right is a map of where we detected different neural structures. So each dot is a neural structure that we detected in its 3D position. You can see the two side lobes of this zebrafish's brain, left and right. And then the colors over time are the activity over time. And this is something that is really hard to do because what you need is single neuron resolution across the entire brain, and fast. You need to do this on the millisecond timescales that these activities are happening on. And this is a really great application for this kind of approach that we're doing because it's sort of natively sparse, and you can in fact somewhat control the sparsity as how you tag the neurons to cause them to light up when they fire. What we really want to go with this is taking this big microscope and turning it into a tiny lensless imager because it's small and inexpensive, and we could put a bunch of them on the brain at different places or next to each other because there's no objective getting in the way. Here's the first sort of prototype of being able to do that. It's just a sensor, some color filters for fluorescence imaging, and then this diffuser on top of the zebrafish sample. And what you're seeing in the video is neural activity in this zebrafish over time. And we're getting approximately single neuron resolution here. So this is sort of a first step and pretty exciting to be able to do this after a lot of years of talking about it. But I want to talk a little bit more about the diffuser. So I showed you this diffuser pattern like this caustics, and this is from a Gaussian diffuser that's off the shelf. We just buy them from Edmund Optics or Newport or Thor Labs. And it has a Gaussian surface shape. So it creates this like sort of random focusing effects here. This is very different than a lens, right? So a lens, you want a sharp spot. So you don't get any multiplexing with the lens because you have just this one spot. So if you don't measure that pixel, you don't measure that spot in the scene. So the multiplexing is good, but what's bad about the smooth diffuser is that you spread out the light across a lot of area. So as you go to deeper depths, the lens also spreads out light, and that's bad. But we're certainly going to suffer some SNR hit to get this multiplexing effect, and we have to trade these off carefully. So originally we were using these Gaussian diffusers. You could think about using a microlens array. So light field imaging uses this. In fact, this whole project started as a question of whether we could build a light field camera with diffuser instead of microlens array. And the microlens array has the advantage that you focus the light into small spots. So you're concentrating the light better, which is better for SNR. When you talk about getting hit by Poisson noise, it's better for SNR, but it's got this problem where if you shift the point source, then you get these ambiguities where if you shift it by exactly one period, then you can't really tell the difference between these point spread functions. So that regularity is very bad. So here's an example where you get this degeneracy. So we want these, we want to look at randomly spaced microlenses. So we still call this a diffuser, even though now it's arguably a randomly spaced microlens. So you've got essentially lenses so that you get sharp spots in your PSF for good noise performance, but they're randomly spaced. So now when I shift them, they're not going to overlap. The other change that we made, or other architecture that we did, was to look at putting the diffuser in the Fourier space of the microscope rather than in the real space. So forget about lensless imagers. If you want to do sort of high resolution microscopy, you're probably going to have to go to putting an objective in there. There's a lot of reasons why it's useful to have this objective. So if you look at this setup, what we've got is the diffuser is now in the Fourier plane of the objective. These two lenses are just relay lenses to image the Fourier plane of the objective, which is inside its housing, onto the diffuser we have here, and then put the sensor immediately after. This is not aperture coding because the diffuser is in the aperture plane, but so is the sensor. The sensor is near the aperture plane as well, so it's different. But what this buys you is a lot of advantages. This makes the whole thing for the microscopy case very shift invariant, which makes everything a convolution. As I showed you for the lensless case, that was already true because things were far away. So now for the microscopy case, we can keep it shift invariant, and we get a huge benefit in terms of the resolution at the native image plane. And so what you're seeing is the lateral and axial resolutions near the native image plane. We can get a really wide range of planes in which this thing stays in focus. So we get a very large volume 3D reconstruction area, and we get good resolution across a big area, which is quite different than light field microscopy. So this is a little bit hard to interpret, but this microlens array, the red line here, is the resolution of a Fourier light field microscope, which has some significant advantages over a regular light field microscope. So we're saying that this microlens array version is already better than your typical light field microscope. And now what you see is this gold line is our random multifocal microlenses, and it achieves a much bigger range of good resolution. So right near focus, it's slightly worse resolution than the microlens array, but away from focus, it does much better. And this is sort of why we wanted to do this, because we can get this bigger range of good resolution. If you think about a microlens array or a light field microscope, it has great resolution at one single plane, and then it degrades very quickly beyond that. So we wanted to avoid that. And it costs you a little bit of resolution near focus or near this ideal plane, but you get much better resolution across a much bigger range. So the other really neat thing that Kyrillos in my group did with this was to build this system architecture into a miniscope platform. The miniscope from UCLA is an open source microscope that you 3D print and put some pieces together. It's really cheap, and it's very heavily used for neuroscience. So these like neural activity tracking experiments I talked about are very often done in this miniscope format because this thing is smaller than a quarter. And so it can be head mounted on a awake behaving mouse while you have it run through a maze or something. So this random multifocal microlens array in the center here, this is just an image of one that we fabricated at Stanford at their nanoscribe, and place this in the pupil plane of this miniscope. So the beauty of this miniscope is that its objective is actually a grin lens, and the pupil plane of the grin lens is just at the other end of the grin lens. So you just like bond this thing onto the end of the grin lens and put it into the miniscope. And then you take out the tube lens of the miniscope and make the whole thing a lot smaller. But otherwise, it's a pretty easy hack on your existing open source miniscope microscope. And then they have this upgrade to 3D that actually weighs a lot less and is a lot smaller than the original miniscope. This thing weighs 2.5 grams, and it's about 17 millimeters tall. So really useful for neuroscience things. And we can get a couple microns resolution out of this. So these are really about 3 microns resolution, and we get it across a couple hundred microns depth, as I showed you before. Here's some captured videos from it. So this is the raw 2D video that we capture on the monochrome sensor. This is sort of for fluorescent sample of, these are tardigrades. They're little water bears from UCSF. You can see this little guy, it's like a little caterpillar. You can see his legs swimming around. And I'm showing you a couple of different perspectives of the 3D reconstruction over time. And this is really cool because what they want to do with these is to get single cell or single neuron resolution. In this case, this is sort of randomly fluorescent, so it's not necessarily neural activity here, but get that across this big volume so they can watch these things while they're swimming around in a relatively large volume. And so we're working with them on pushing this to the next level. So let me talk a little bit about our diffuser design again. So I mentioned before that as you move a point source back and forth axially, what you get is scaling of the PSF. But actually now it's going to be a little bit different. So now because it's in a microscope, we also have like the whole thing is scaling quite a bit over a reasonable range of depths. And so what you see is for a single focal length microlens array. So if we didn't use multiple different focal lengths, then what we would see is there's going to be one plane where all those spots come into focus, and that's a good PSF because it has sharp features. But all the other depth planes have defocus features, which are going to reduce the resolution. So that's why we don't want to use just a single focal length. So what we, you can see the intensity plot here for the PSF profile. It's just a line along this black dotted line. Yeah, so this is the single focal length microlens array. So it's a random single focal length microlens array. And here's the multifocal length microlens array. And you should see the benefit here that at different depths, different spots come into focus. And that's good because it means you have sharp features at all of these different depths, which is what allows you to get good resolution across the wide range of depths. But you can see here there's a lot of going on, right? This point spread function is changing its shape quite a bit. And that's necessary because we're operating with this grin lens here. So, so that's all coming into play in how the reconstruction works. Okay, so I would like this to be the end of the talk, but I think it's actually really fun to talk about all the problems that we run into when we build these kinds of systems. And this is one of my favorite quotes. I stole this from Mike Geim. It's about NASA triple redundancy, can't afford to fail. Compressed sensing, oh, look at all this redundancy, I can fix that. So one of the key problems with typical computational imaging is that you design these systems to be extremely efficient, and as a result, they become also extremely fragile. that when you don't have the perfect A matrix, when your assumptions aren't perfect, they can have really weird artifacts. And so I want to get into some of the weird things about this DiffuserCam imaging system. So this is in relation to the lensless version here. If we try to define the resolution of our system, we see weird things. So if I look for the 2-point resolution, typically an imaging system, if you want to know its resolution, you just look for the 2-point resolution. So we did that. We put 2 points as close as possible together and see how well we can resolve them. And then we said, okay, this is 2-point resolution. It varies with depth because this is a non-telecentric system. So the absolute numbers here are not really important. But what is important is that if I take that 2-point resolution and try to reconstruct a 4x4 grid of points, it just completely fails. So this is in XZ. So this is at the 2-point resolution, but in XZ dimensions. I'm putting a grid of 4x4 spots, and it just doesn't work. So this 2-point resolution is not predictive of the 16-point resolution. And that's because we have this nonlinear reconstruction algorithm that enforces sparsity, and the 16 points is less sparse. And so it doesn't do as well. And so what do I have to do to resolve these 4x4 grid? Well, if I go to 1.6 times the 2-point resolution, then I can now actually resolve all of these points. Okay, so is 1.6 times the 2-point resolution the actual resolution? Well, not really. If it gets less sparse, then the resolution may get worse. And we want to be able to talk about resolution, sort of like what's the resolution of our system? And this is really sort of like a confusing piece because it's not a linear system, so we don't get to just use linear system metrics for resolution. But we can really consider this 2-point resolution is a best case scenario. So that gives you a chance to tell someone what's the best resolution you could ever achieve. But we also want to think about what's the likely resolution you're going to get in the real world. And we don't have a good solution to this. But what we did was we wanted to use condition numbers. Condition numbers are really for linear systems. So we just invented this local condition number of the sub-problem. And I think I've seen things like this before. But the idea was that we looked at the condition number of the problem that you would solve if you knew where there were non-zeros. So where the sparsity, where the non-sparse elements were. If you knew where the non-sparse elements were, pick out all those columns of the A matrix and then solve the inverse problem on that. And that is a linear problem. So then we can talk about a condition number for that. So this is also sort of assuming that you know where the non-sparse things are, but that's a separate problem that you would also have to solve. But we saw some trends here that I think are interesting. And the idea is that if I have 2 point sources, 50, 100, so I'm drastically increasing the number of point sources. And of course, the condition number gets worse. And it also gets worse as you go to smaller separation between those points. But what you see is it starts to saturate, that it's not getting that much worse as you add more and more points. And so if you think about the sort of saturation effect, that's why we showed you the 16 points is sort of around the area of where it starts to saturate. So that's roughly a sort of a worst case scenario. Although there's a lot of caveats there, but it can give you a sense of real world performance. Okay, so the other challenge is model mismatch. And I pretended like everything was great and we had this perfect shift invariant system. But in reality, actually what you see here, as you go off to sort of higher angle parts of the image, then actually it becomes less shift invariant. So inner product similarity is a great metric of how shift invariant the point spread functions are at different lateral positions. So the lateral positions are here in degrees because we're looking at the lensless non-telecentric system. So the field of view can be thought of in terms of a spread of angles. If you look at the normalized spot size of the reconstruction, this gives it a pretty good sense of resolution at these different field positions. And we've been using this convolution model, which is not exactly correct, particularly near the edges. And this is basically what you're going to get. This red line here is what you would get if you like exhaustively calibrated this thing. So the gap between this blue and red lines is what we're losing by using the convolution model. And we think it's totally worth it because of the massive benefits in computation you get from having a shift invariant model that's just a convolution. But the other way you can go is to just design your lensless microscope to have a small range of angles. So you can spread your resolution across a smaller range of angles. if you're okay with that and you don't need a wide angle camera, then that works great. And you just don't have to deal with this model mismatch effect. If you want to do microscopy with the lensless version, so that microscope I showed you with the lensless version, it's very non-convolutional. And so you have to deal with it. And so Grace built this microscope. And if you try to use the convolution model, this is a video of beads flowing through a microfluidic channel. And you see like all kinds of crazy artifacts in this without the local convolution model, whereas she's corrected them all computationally with this local convolution model. And the local convolution model is exactly what you think it is. It's modeling the point. So we measure the point spread functions across at different points in the field of view, and then we sort of interpolate them across the field of view so that you account for the fact that there's a different point spread function at different points of the field of view. Okay, so let me get into the reconstruction a little bit. So so we have this data fidelity term here, so y minus ax, and we're basically trying to minimize the difference between the measurements we take and the measurements we would have taken given the forward model. So this forward model can be convolutional or non-convolutional, whichever you happen to be using. And then under the argument, I have a positivity constraint because we don't have any negative light. This just helps us constrain the problem a little bit further with realistic assumptions. And then this last term is the compressed sensing term, where we reinforce sparsity. Almost everything I'm showing you, we're using TV sparsity or 3D TV sparsity, but you can adjust it at will depending on what your particular application is. So this is a big nonlinear optimization algorithm. As I said, we use ADMM. You can use FISTA, various different approaches, but all of these different approaches I think of as, I'm going to call them physics-based image reconstruction or model-based image reconstruction, because you're using the physics of the known A matrix to basically define the inverse problem and solve this optimization. Put in your measurement, pop out the final result. So the other way to go about this that's becoming popular is to think about deep learning approaches. So let's forget all the physics that we know, do a whole bunch of training on measurements and images, and then train a network to learn the physics so that you can put in your measurement and pop out your final result. And I have a lot of thoughts on these different approaches, but I like to think of them along a spectrum. So these physics-based like FISTA, ADMM, gradient descent, optimization-based methods are great because they are interpretable and robust. They use the known physics, but they can be really slow, and this model mismatch like always causes problems. If you do deep learning reconstructions, one huge benefit is they can be fast, and they can learn this model mismatch and try to fix it. But they also can do strange things, and they need big training data sets. So where we wanted to go is trying to do best of both worlds, to use the physics we know and learn the stuff that we don't know. And physics-based learning, I think, is a really interesting and popular topic these days in computational imaging. And for us, we've seen that it gives us a lot of basically efficient parameterization. And I like to think of it as using the known physics to design the architecture of the neural network such that it becomes really efficient. We can get away with a lot, orders of magnitude less training data to get a high quality result. So you use the physics you know and learn the stuff you don't know. And that just seems sort of academically more satisfying to me than trying to learn everything with deep learning. So the way that Christina did this for our DiffuserCam was to take that ADMM algorithm, the iterative algorithm, and unroll it. So she makes a neural network where each layer of the neural network is one iteration of the iterative optimization algorithm. And then at the end, she has some loss function and she go forwards and backwards, right? So this is really cool because you're baking into the architecture of the neural network the physics that defines this ADMM solver, but you're learning as many parameters as you like about the solver, or you can put a unit at the end to just to clean everything up afterwards, and then you've got learning a lot of parameters. So she explored the spectrum between physics-based learning and deep learning. In her paper that you see here, there's a lot more details, and you can see a few more ways of balancing physics versus deep learning and seeing the relative results along the spectrum. So what you see in this result is that the physics-based reconstruction is slow and it has lots of artifacts. The deep learning-based reconstruction is fast, but it also has just different artifacts. And when we put the two together in this sort of like partway along this spectrum where we use this unrolled physics-based learning, we can get fairly fast reconstructions with much higher quality. So we're getting faster and higher quality. And that was the whole point. It's about 20 times faster. And I've lost track of how many training data images we used here. We had 24,000 to start. So this is the end of my talk, and I'm going to be happy to take questions. I think one theme that I really wanted to get across, and this DiffuserCam project fits really nicely with all the other projects in my lab because it's extremely reproducible. And for computational imaging, where it's all about the hardware interacting with the software, reproducible doesn't just mean posting your code open source online or commenting your code nicely. It means that you make both the software and the hardware accessible. And by accessible, I mean, you can give away the code. You can give away the code and make it easy to use, but you can also make the hardware easy to use by making it cheap and simple so that somebody else can actually build this thing. And one of the big things we've been working on is trying to push these methods to be very user-friendly in terms of hardware. So we really avoided trying to make you buy an AFM or do a 2-day-long calibration procedure or use the cloud to have to do your reconstructions, because we want this to be very accessible for people to build easily in their own labs. And if you want to do so, we're very happy to help. And we love to hear about people who build these things based on our open source designs. So I thank my group who did all of this work and all of our collaborators. Happy to take questions now.
Okay, thanks, Laura, for the talk. And the way we would do this is we have attendees posting questions in Q&A, and you should be able to see the Q&A as well. Okay. And I could read the questions, so you could answer once I read them.
Sure.
Or you could read them. It's either is fine. What would you prefer?
It doesn't matter. I can read them, I guess. So first question is, I can see shift invariance in XY. What about in Z? There's always been the most difficult item in classic deconvolution. So yeah, I showed you, this maybe came early. So I showed you how much shift invariance there was in XY. That also completely depends on your design. So if you use very smooth diffusers and you design, basically you design your pixel sampling and your distances from the diffuser such that you have a really narrow range of angles, you can have very little shift invariance. If you want to bring things closer, you want to do things smaller resolution, then you need smaller pixels, and then you need smaller features on your diffuser, you need to bring it closer, then you're going to have more shift invariance. So in Z, it's not really, we never said it was shift invariant in Z. So in Z, what's happening is this point spread function is scaling, and it's not a perfect scaling. So if you take the stack, so we did this, you take I wish I had the images handy, but if you take a stack of point spread functions along Z and then rescale them appropriately and look at that video, it's very different. It's changing subtly, but it's changing enough that it's not going to work to just to scale your PSFs arbitrarily. So you can only go a certain distance of scaling the PSFs typically. And in practice, we very often measure a whole stack at different Z of these PSFs if you want to get a very good reconstruction. So the deconvolution is still treated like it's only a convolution in XY, and then each Z has a different deconvolution kernel. So it's so it's not a 3D deconvolution is what I'm trying to say. And okay, so I hope that answers that question. The next question is—
So Laura,
sure.
We are also giving the attendees the option to ask the questions live. And so what I would do is whoever's name is on the list, I would turn on their mic in case they wanted to ask a question themselves or ask any follow-up. And so I've turned on Kevin Ryan's mic in case he wants to ask anything.
Okay.
Yes, thank you very much. I typed in my questions mid-lecture, and I have to say you really answer them quite clearly during the presentation. Both the first one on shift invariance and the second one about randomly placed or randomly blanked out uniform microlenses. but I think you covered that with the range of Z resolution. Thank you very much on that.
Okay.
Okay, so the next question is by...
Actually, I would love to answer this question. Maybe I sort of answered it, but I'd love to expand on this one question from Kevin saying, could the randomly spaced microlenses be replaced by uniform microlenses with random blanking to distinguish degeneracies? And actually, there's a technique called Fourier integral microscopy. It's basically, integral microscopy is the same thing as light field microscopy. Fourier means they put the microlens array in the Fourier plane. So it's like exactly what we have, except with the uniform microlens array. And then because of this uniform ambiguities, they can't do compressed sensing. But so what they do instead is I don't know what random blanking means, but basically they just clip the field of view so that the field of views don't overlap. So then effectively what you see on your sensor is a grid of measurements taken from different perspective angles. So it's almost exactly the same as a camera array in photography. And you can do that and it works great. It's like a light field measurement, but the loss is that because you didn't let those fields of view overlap, you end up with a really small field of view. So if you use 9 microlenses in the Fourier plane, you have to cut your field of view by a factor of 9, which is really painful. All right, you can move to the next one, sorry.
Okay, the next question is by Andre, and I have, okay, I think he does not have mic. So Laura, you could just read the question and answer.
Sure, so the question is, would it be possible to consider an atmosphere as a diffuser or is it too thick? It's a great question. I don't really know. I think the problem wouldn't be that it's too thick, but rather that it's changing. And so we need to do this calibration measurement and then have it be applicable for the reconstruction. And so I think that might cause problems. You also might see, if you're talking about using atmosphere, so you can do astronomy, you have to think about SNRs. I don't know relatively how dim like the light is in those cases relative to, so some of the fluorescent imaging we're doing is pretty dim and does have significant background, which would definitely be a problem in astronomy, but I don't know relatively which is dimmer. So you might run into SNR issues, or it might be that it's changing, or maybe it works, I'm not really sure.
Okay, so next question is by Elakia Shivakumar, and I've enabled him to speak, but I do not know if you would like to ask the question directly.
Hello.
Hi.
Yeah. Hi, ma'am. I love this thing. My question is, how will you be able to say which part of the brain you are measuring the firing from by using these mini scopes for a single neuron measurement? And the other question is, how do you, because the brain, the neurons fires simultaneously because of synapticity and all, how do you say that it's from a particular part of the brain? I mean, how do you prevent interference?
You mean like a particular part of the, like, so we do a 3D reconstruction, right? So if you have one of these mini scopes, typically you're going to like surgically implant it in a particular part of the brain. And then we're just looking at a few 100 micron area around that. So we know like what area of the brain. If you mean like within that hundreds of microns volume, how do we know where it is? Well, that's what the 3D reconstruction is for. So you know which neuron it is. I'm not sure if I'm interpreting your question correctly.
Okay, so Elakia, do you have any follow-up?
Hi. My question was, what about interference? Because it's from single neuron. How do you
What do
avoid
you-
interference?
What do you mean by interference? Like optical interference?
Because there's going to be multiple neuron firing. How do you avoid interference between firing of neurons and?
Well, because we're doing a 3D reconstruction, if there's multiple neurons firing and we have single neuron resolution, then we should reconstruct that these two neurons were on at once. So the reconstruction will be 2 points.
Okay. Okay. Thank you.
Yeah, thanks for the question.
Okay, so the next question is by Daniel, and I have enabled him to speak. Daniel, if you would like to speak. We can give them a couple seconds. Otherwise you can read the question and answer, Laura.
Yeah, so the question is, early on you had an example of shift invariance in which two views didn't stitch together too well. This suggests a lot of these problems aren't truly shift invariance. Instead, they might be more stereo in nature. I'm not sure what you mean by stereo, and I'm not sure which one you mean stitching together too well. So I'm showing my slide deck so you can point to which slide. But I did show later that they aren't truly shift invariant and how we deal with it with this local shift invariance method. So hopefully that addressed it. I will say, like, the local shift invariance method is much more computational, and it's you have to take measurements at a grid. You have to take calibration measurements at a grid of points. So it's not super practical for like doing at home or something. You could do it in the lab where you might have a motion stage, but you don't want to use it unless you have to.
Okay, so unless there is any follow-up on that, we would like to proceed to the next question, which is by Bernal. And I've also enabled him to speak if you would like to ask his question.
It looks like he's still on mute.
He's still on mute, so I guess you can go ahead, Laura.
Sure. So the question is, besides sparsity, what is the fundamental difference with classical algorithms for blind deconvolution? I motivate this to address systems where we do not have prior knowledge of the system. Okay, so what we're doing is not blind deconvolution. We're measuring the PSF. So in the 2D lensless DiffuserCam case, we know the kernel that we're deconvolving, so we're not doing blind deconvolution. In fact, I've been trying to get my students to do the blind deconvolution problem on this forever, and Grace is finally getting it working. It's not as straightforward as I would have thought, but basically the idea is take a video while you wave the camera around, and then you have like n images, and you need to solve for n+1 things where you solve for the n images plus the point spread function. So I want to do that, but we're not doing that. So it's not blind deconvolution at all. And so we don't have prior knowledge of the system, but we have prior knowledge of the system response at one point, and we're predicting the system response at all the other points from that one. So it's sort of fundamentally different in that sense.
Okay, so maybe we can go to the next one. Laura, the next question is by, pardon me if I'm not pronouncing it correctly, Slava. And I've enabled Slava to speak if they would like to ask the question.
I can read it if not. So the question is, you presented different randomized diffusers. Do you think one can consider a learnable diffusers matched with the image's objects? And yes, absolutely. We're working on this. We've been working on this for a long time. We want to do end-to-end learning where we do this like learned, unrolled optimization, like what Christina did, but also in conjunction, learn the best diffuser to go with it. So what you would want to do is learn the surface shape of the diffuser to make it optimal. The memory footprint of that is insane, particularly for the 3D problem. It's really not very feasible. what we've done is we've parameterized it. So one of my students has a background in optical design has some really good arguments, convinced me that it should be random, it should be lenslets. And so if we parameterize by lenslets and just learn their focal lengths, apertures, and offsets, then we reduce the parameter space a lot. And so that's what we're doing. And we have some results on that. I don't have slides on it yet, just because I'm not convinced we have the final answer yet. And we haven't actually fabricated these things. So fabricating them to spec is a little bit difficult. That's been one of the benefits of DiffuserCam, is that you can use imperfect optics, and it doesn't matter because you're going to characterize it. It'll just be not ideal. So what I can say we've learned is that, okay, so with this might change our conclusions, but so far our conclusions are that doing this end-to-end learning doesn't change the design too much, that our heuristic design was actually pretty good. And we used some sort of like cross-correlation metrics to do a little bit more than a heuristic design. And that turns out to be really good. And so I really am trying to get to the like final answer of what's the best diffuser for a given volume that you would like to look at and a given sparsity. And or you could potentially do this on different types of objects or different types of sparsity. So we want to do all this. It's hard because of the computation. You run out of memory, and we're working on that. And I hope to have an answer for that soon.
Okay, so there is, I think the next question is actually from Kevin, again, Kevin Ryan, and I've enabled him to speak if he would like to ask.
I was just sending, this is primarily for the lecturer, but my question about random blocking seemed to be ambiguous. So I filled that in for what I meant by random blocking of the microlenses to remove the degeneracies, blank out some of them so that there is actually a distinguishing feature between the degeneracy shift from one lens set to another, or put an aperture on the entire array so that if the entire array is shifted, you know what the shift is in X and Y. But that was just to fill in on that. Your answer about the different focal lengths providing different sharp points was, I think, very clear answer on that as to why the randomly spaced uniform focus was not a good idea.
Yeah, so the random blanking, now I understand what you mean. That could work. It's just you're blocking some more light and it would be a little harder to fabricate.
So not a question, just information for her.
Okay, thanks.
All right, thanks, Kevin. The next question is by Venkat.
Laura, this is Venkat. Very nice talk. I had a quick question about, so it was found the discussion on the resolution very interesting, right? So that's one of the challenges typically with these, when you have more complicated priors, is that it's difficult to define like what the final resolution will be in general with these optimization techniques. But for the applications, you're looking at how important is it? Like, are end users looking for a number, and or is it, how big a priority is it from
anyone? Yeah, it is a big problem, and largely it's a problem of communication, because a biologist who's thinking about using our technique and asks us the resolution, if I start being like, well, you can get this, but you're probably going to get this, and it might be this, it depends on what your object is, then they kind of get like, do I really want to work with this person that doesn't even know the resolution of their imaging system? And so I think there's a big issue there. So if you look at we've targeted some very specific applications like the neural activity tracking, in part because I think they're very well-defined objects that we can design around. And that's what we have been doing, is designing for those amounts of sparsity and they need single cell resolution. They need to distinguish this neuron from the one next to it. Beyond that, they don't care. And neurons can be fairly big, a couple microns at least. In mice, they're, tens microns. And so it's not really difficult resolution to get, but it's really important that they get that. And sometimes it is difficult to get that if you're trying to go after a big volume. So yes, I think it's true, particularly for the applications we're working with. And it's a big like communications problem because it's very difficult to characterize a system when the system depends on the object that you're imaging.
Thank you.
I would love to have more theory, better theory, how to like explain this or deal with this.
Right. Thank you.
Next question is by Slaver again. Laura, would you like to just read?
Yeah, so it says, and what about optimized sampler spatial? Does it include it too? I'm not sure what this means, like optimized spatial sampling of the detector or of the diffuser. So it certainly very much matters how many microlenses are in your diffuser, which basically sets this average size of the microlens. This is a really important quantity, and this end-to-end learning I'm talking about, that's the most important thing that it seems to learn is how many diffusers to put in the diffuser pattern across the aperture. So, and it totally depends on the situation that you're looking at and the resolution you're aiming for. If you're talking about spatial sampling of the sensor, you basically want the sensor to Nyquist sample whatever point spread function you have. So it's a little bit tricky sometimes to find diffusers that create caustic patterns that match the sensor sampling, but we just have this sort of like big spreadsheet of different sensors that are available and all their different properties. Then choosing the sensor can also be important for quantum efficiency if you have dim light. And one other thing about the sensor that really matters is that some of these, so the backside illuminated sensors are much better than front side because they don't have circuitry in the way that cause angular dependent response of the sensor. So if you're doing any of this lensless stuff at angles beyond 15 degrees or so, then some of the sensors start to behave strangely at those high illumination angles. And you don't want to have to take that into account computationally because it becomes a big mess. You can, but back illuminated sensors seem to be just easier to deal with. So we do think carefully about what sensor we use.
Okay, so the next question, I hope, pardon me if I'm not reading the name correctly, is by Musuk Jang, and I've enabled him to speak if you'd like to ask this question.
It keeps looking like the person is unmuted when you.
Yeah, I think some of the attendees may not have their mic turned on, so I think that's the case here. So maybe Laura, you can just read and answer.
Yeah. The question is, in my understanding, DiffuserCam generally improves the number of optical modes you're imaging with the limited number of 6 physical sensor pixels. Instead of using the DiffuserCam for extending field of view or adding third dimension in depth or time, would there be any chance to use similar concepts to improve the resolution? Yeah, so basically, instead of trying to get higher dimensions, can you improve the resolution? We sort of tried this. It doesn't really work out that you can just take a single image to improve resolution. So what you'd want to do that is you want a diffuser that has features smaller than the pixel size. So if you're doing this lensless version, you can improve the pixel resolution, but you can't improve the optical resolution because it's fundamentally limited by your aperture size. If you want to improve the optical resolution, you need to go to like a real microscope and put the diffuser in the real space and the sensor at the image plane, because you need to you need to put the diffuser in a place where the resolution information, the higher resolution information is there. So for example, if you're trying to do optical super resolution, you need to have the diffuser close enough that it's interacting with the evanescent fields of the sample. We try to do this. It came with a lot of problems. Doing this, like putting a diffuser in the evanescent field, is extremely impractical. You need very tiny features on it. And there's some work from a few other places I can send you by email if you like, that did do this successfully, but it's very difficult setup because everything is so tiny. We tried to do this to try to beat the resolution limit of the diffraction limited microscope, with a 0.1 NA or so. So taking a low resolution microscope and trying to turn it into a high resolution microscope by putting a diffuser in the real space. We put a piece of Scotch tape. We had to take multiple images to get this to work. And you can see a paper by Li Hao Ye on that. That was sort of like what we were attempting to do, but it turns into a fairly different system because you have to take multiple images and scan the speckles as your illumination.
All right, so the next question is by Varun Kelkar, and I think he would like us to just read and answer.
I should read it?
Yes.
Okay, in the cheap homemade cameras, what is the contribution of the Porse sensor to the reconstruction artifacts? If there's a lot of error due to quantization, what are some approaches to doing quantized compressed sensing to improve the reconstruction in the homemade diffuser cams? So I don't really know what's the relative contribution of using Scotch tape instead of a properly designed diffuser versus the contribution of using a terrible sensor like the Raspberry Pi versus the nice SCMOS cameras that we sometimes use. If it's due to quantization, you should be able to just average a couple of images if you have a static scene. And that definitely helped us. But the cheap homemade cameras it was an undergrad project. They were mostly focused on getting it working and getting the tutorial going. So we didn't do too much analysis of, what was causing the various different artifacts. So I don't really know.
Okay, so the next question is by Ray Vargas, and I have enabled him to speak. So maybe we can give Ray a couple seconds and then you can read the question.
Okay, I'll read it. So please suggest one good reconstruction method.
Oh, no, it's the one before. Can you use a digital micromirror device in place of the diffuser?
Oh, can you use a digital micromirror device using compressive sensing cameras in place of the diffuser? You certainly could. Digital micromirror devices are reflective, and so there'd be a lot more optics and it would take up a lot more space and you'd have a limited range of angles. It would also be an amplitude mask. So the advantage is that you could dynamically change the coded pattern. I think this would just become much more like just a coded aperture camera, and probably that's been done before. I think one of the cool things of the DiffuserCam is that it's like sort of phase mask, which is light efficient, and it can be just sort of shoved in an existing imaging system to make things really practical. But yeah, you could do that. And if you could take multiple images, I'm sure you could do something better with it, like higher resolution, etc. And I think there is some work along those lines.
Okay, so yeah, the next one is from Rajeshwari, and I have also enabled her to speak if she would like to ask the question. If not, Laura, you can go ahead.
Looks muted, so I'll read it. Please suggest one good reconstruction method when compressed sensing is used for biomedical images. So one good reconstruction method, I guess like FISTA has certainly been used in biomedical images. ADMM, I think ADMM is kind of the sort of the go-to reconstruction method right now. There's probably others on this call who have better answers than me for that one. That seems to be all the questions.
So there were a couple questions that some attendees posted on the chat rather than in the Q&A, and I can read them. So it's there is one from Pooja Gupta, and the question is, do you put the point sources practically and then calculate the condition number?
Sorry, do you put the
point sources practically and then calculate the condition number? I assume she means if this is an actual experiment.
Oh, so the condition numbers are all calculated. It's just computed. There's no experiment that goes with it. the 2-point resolution that I show is a real experimental measurement. And we want those to match, and they sort of match.
And the next question in the chat, I think this is the last one. It's from Samuel. And it is known that a lensless imaging system is the most efficient setup in terms of light. However, I was curious if you have analyzed your system under darkness conditions in order to identify its performance in terms of reconstruction quality.
Under darkness conditions?
Yes.
I'm not sure what that means. Certainly, okay, so the diffuser is collecting whatever light gets to it. So it's effectively collecting the same amount of light as a lens camera with a lens of that size. It's actually one cool direction to think about is to going after, and there's some people at Rice looking at this, like to going after like a really big aperture because you can collect a lot of light relative to like what a super expensive bulky camera would be able to do. It then focuses the light into multiple spots on the sensors. Then you have to think about if you have Poisson noise that hurts your SNR. So yeah, these things have to be traded off.
Okay, I'm not sure if this was posted in Q&A from Andre. It is possible to use optical amplifiers and super resolution for the images so SNR can be improved. I guess this is just a statement.
Okay, sure.
In fact,
Okay.
there is one more question from Pooja Gupta. I saw that. Can we use a diffuser for imaging NIR region?
For imaging which?
Near infrared region.
Oh, yeah, that could be really fun. If you can make a diffuser for near infrared, then sure, you could do this. So we actually tried this in X-ray. Some of the folks at Lawrence Berkeley Lab, some of my students work on X-ray imaging and realized that they're looking at photolithography mask. And if you use a mask blank, it happens to be a pretty nice diffuser because everything is rough on the scale of X-ray wavelengths. And so we've tried some of these tricks in X-ray because we happen to have diffusers there. So it just depends on if you can have diffusers in that wavelength range, which I think you can.
Okay, I have enabled Pooja Gupta to speak if she has any follow-up.
Hello.
Hi.
Hello.
Hi, we can hear you.
Yeah, we can hear you.
Hello. I got the answer. Hello. Thank you so much.
Okay, thanks.
Okay.
Thank you. All right, so we have also been live streaming this on YouTube, and Jong has been monitoring that. Jong, are there any questions from YouTube?
I was on mute. Yeah, no question from the YouTube at this point.
Okay, so then I think we've gone through all the questions. And so let's thank again Laura Waller for her wonderful talk on microscopy. And for the attendees in general, the next talk would be 2 weeks from now, the Tuesday after next Tuesday on the 16th. And it would be by Michael Unser from EPFL. And again, everyone has to register at the Space Webinar website using the link, and then you will be given the Zoom link to attend the next seminar. And also, we will be posting the recording of this seminar, and the link will be made available on the Space Webinar website. And we might also post the slides based on once we get once the speaker gives their nod to posting their slides, and in that case, the slides will be posted on the website of the webinar as well. And that's about it. So unless anyone has further questions, in which case you can post that on the Q&A. If not, I would like to thank you for attending our second webinars in this space webinar series, and we look forward to seeing you another time soon. Thank you. Bye.